I'm sure you're already familiar with scalar math. It's the normal addition, multiplication, and so on that you've probably been doing for most of your life. But sometimes, like with neural networks, you might need to perform those sorts of operations on a lot of numbers. Maybe hundreds, thousands, even millions of them. Maybe you need to double them, square them, or divide them all by the same number. If you were writing a program, you might decide to make a loop where you iterate over every value and perform the same operation on each one, over and over. But matrices offer a better alternative. If you have all those numbers stored in a matrix, you can perform element-wise operations on them. That just means you'll treat the items in the matrix individually and perform the same operation on each one. By the way, I say matrix, but this notion of element-wise math applies to data with any number of dimensions. To add two scalars, it's easy, like 2 plus 3 equals 5. To add a scalar and a matrix, it's practically the same thing. Just add the scalar to each of the items in the matrix. So 2 plus the matrix 1, 2, 3, 4 equals the matrix 3, 4, 5, 6. You can do the same thing with other math operators too. Here's a real-world example. Let's say we have a matrix of values that represents the red color channel of an image. Assuming we're using RGB colors, each value will be a single byte ranging from 0 to 255. But let's say we want to normalize these values and convert them all to floating point values in the range from 0 to 1. Easy. We just divide the matrix element-wise by 255. By the way, don't worry if you don't know what normalizing means. You'll learn more about that later in the course. And this doesn't just work with scalars and matrices. You can also do element-wise math between all the elements within two different matrices. For this to work, the matrices have to be the same shape. For example, here we have a pair of 2 by 2 matrices. To add them together, we just add pairs of numbers that are at the same indices in each matrix. And then we store the result at the same location in the answer matrix. So at index 1, 1, we'd have the result of adding the 1 plus the 2, which is 3. And at index 1, 2, we'd have the result of adding the 3 plus the 4, which is 7. And so on. Now just like before, how I said you can do any normal math operations element-wise between scalars and matrices, you can also perform any of those operations between corresponding elements of two identically shaped matrices.